Okay, here we are, section 2.2, limits involving infinity, day 2. We're going to be discussing infinity again, but this time not as x approaches infinity, but rather as we approach a local value, answers that could turn out to be infinity or negative infinity. Okay, so basically we're coming back to the whole idea of left limit, right limit, coming in from the right, coming in from the left, that sort of thing, one-sided limits. But we're dealing with answers that come out to infinity rather than studying the graph behavior out at infinity. Okay, so that might be more clear later if that wasn't clear already. So we're back to doing limits as x approaches a value, not infinity. All right. What I have here is a rational function. It has a domain restriction here at -2, so this function actually has an x plus 2 on the bottom. Its only root, its only x-intercept is at -1, so it would stand to reason that the numerator would be an x plus 1, and just for reasons of accuracy there's a minus here. This is a function that I just came up with. It has a horizontal asymptote also. It's actually at y equals -1. Y equals -1 is a little hard to find on here because this is set off in increments of 5. Okay, but you're welcome to draw it in if you like. If you want to pause the video and draw yourself an asymptote running right through -1 there. Okay, the window is listed here, but it's pretty clear from on here as well that we're basically going from -5 to +5, well, 4, and then -25 to +25. Okay. So let's talk about the limit as x approaches, and then this point here, -2 seems to be interesting. It's got that asymptote. And we're going to be coming from the left side, so we use the superscript minus, remember, for our given function. Okay, so for this we're following an arrowhead. Imagine traveling along this graph, and in your efforts to reach x equals -2, which by the way will never happen. You can't actually cross over. You cannot cross over a vertical asymptote, although you can for horizontals. We're dealing with this graph dropping down towards -infinity. So I'm going to go ahead and put -infinity there for that. Alright, let's take a look now at the same problem. This time a limit from the right. So we're going to approach -2, but from the right side. So there's a little superscript plus there. There's our function. Okay, let's go back up here and look. Okay, you can see the graph climbs toward infinity as we come from the right. So remember the plus means from the right. So this goes to +infinity. Okay, so we have two answers on this one, and that's never, that always means basically the same thing. If you have two answers, you're dealing with what we call it does not exist. So let's go down here and let's write our final conclusion in here. Since these are not equal, our conclusion is that at -2, the limit of negative x plus 1 over x plus 2 does not exist. D and E. Okay. Well, we can come over to this next one. What I did here is I took off that negative that was in the front, and that flipped the graph over. Okay, so let's do our work over here. And essentially just reverses a couple of our answers, but let's just run through it real quick. Okay, so I went ahead and kept my vertical asymptote here. The only difference is actually that this is completely upside down compared to the other. It even has the same point there. Okay, so it still has the x plus 1, it still has the x plus 2, and that explains the x-intercept at -1, and it explains the vertical asymptote at -2. Okay, so if we're approaching -2 this time from the left, you can see that this time it actually goes upward, towards infinity if we're approaching -2 from the right. So we use a superscript plus there for -2. The graph is dropping downward. It's -infinity. These are not equal. So in general, the limit as x goes to -2 for this function does not exist. So you might say, well, why are we even doing it if it doesn't exist? Well, it doesn't exist is just as important as any other problem. So just because we have problems with, no solution, infinite many solutions, does not exist, doesn't make the problem worthless. It means it's just different. Okay, so what exactly is a vertical asymptote? We know intuitively what it means. We've been seeing those all through pre-calc. Basically, the line x equals a, which by definition is a vertical line when it's x equals number, you remember that, is a vertical asymptote of the graph of a function y equals f of x if, and then either of these have to be true, either the limit as x approaches a from the right of f of x equals infinity or -infinity, or the limit as x approaches a from the left of f of x gives us an answer involving infinity. So basically, if an answer is infinity or -infinity, and this down here is a number, a constant, then you're dealing with the vertical asymptote, and it can be either of these scenarios. Okay? Okay, so now we're going to be finding vertical asymptotes for various given functions, and we'll be describing the graph's behavior on the left and the right of the asymptotes. Okay, so for the first function, I just went ahead and said the domain is all real numbers. X cannot equal 0, so all real numbers except 0. And so I determined that this was a vertical asymptote. Now I know that it's a vertical asymptote because it's the restricted domain value, and the numerator doesn't reduce with the denominator. So this x equals 0 domain restriction is here to stay. Sometimes we have a chance to cancel out things that make 0 on the bottom, but that's not going to happen here. Your other option is to graph it on a graphing calculator. It's similar to 1 over x, except that it's steeper and it's also symmetric on the y-axis. It's an even function. Okay, well, in any case, you can come over here and plug in, or do your limits. We're doing limit from the left as x approaches 0 from the left, because that's 0 is a vertical asymptote. And we're doing that by just inspection here. You can see the graph goes up on the left. So this is infinity. And if you're coming from the right, it goes up as well. So that's infinity. And these two agree. Okay, so we found the vertical asymptote, and we looked at the left and the right hand limits. Let me make a quick comment on this. If you didn't have a graphing calculator, you could certainly make a table and graph this. You only need a few values before you realize what's going on. The other thing, though, is it kind of makes sense, because it should make sense to you, because you're basically taking 0 and plugging it in to a denominator. Now you can't do that, but we're approaching 0 from the left. So we're taking small values and we're putting them in and squaring them before we do divide. So if you were to put in, let's say, let x equal -0.1, then you're essentially evaluating 1 over -0.1 squared. Well, that's right there. That's 1 over positive 0.01, which is 1 over 100th. So it's 100. It's already a fairly large value. if you were to go with 1 over negative 0.01, this is 1 over, and it's positive here, 0.0001, or 1 over 10 thousandths, 1 10,000ths. So this is 10,000, see? So just by coming in towards 0 from the left, numerically, we're dealing with values getting infinitely large towards positive infinity. And of course that wouldn't change if we were to let x be, I forgot to write this here. That wouldn't change the fact that if we were plugging in positive 0.1 and positive 0.1, that certainly wouldn't change these numbers here. So anyway, plugging in a small value and dividing it under a 1 is going to create large values. Okay, this is more formal though to show your work there. Alright, good. Let's look at this one, tan x. Okay, so we're trying to determine the vertical asymptotes here. Well, tan x doesn't look like a fraction, but if you remember what tan x actually means, it's sine x over cosine x. And these do not reduce with one another. So basically we have vertical asymptotes wherever cosine x equals 0. Okay, so either from the unit circle, or from just doing a quick inverse cosine a couple times in the calculator, or hopefully from your memory, we know that this represents 90 degrees, 270 degrees, 450 degrees, and so on. In other words, odd multiples of 90. So we would call that 2n plus 1 times 90. Okay. And we should probably be comfortable using radians here. So instead of 90, we should be willing to use pi over 2, right? Okay, so, but nonetheless, we know that there are vertical asymptotes, and there are a ton of them. There's also one at negative 90, negative 270, negative 450. We have a coterminal, anything coterminal to these. Alright, so our conclusion then is that we have all of these vertical asymptotes. So we'll just put this, vertical asymptotes at x equals 2n plus 1 times pi over 2, where n is any integer. Okay, what do those look like? Well, the actual graph looks almost like a cubic, but it's bound between adjacent, bound between an asymptote at 90 and one at negative 90. And this is the fundamental period for a tan graph. And there are many other branches, as you know, they just continue on forever. They just go on. Okay, so the point is, if you're going to be approaching from the left of the asymptote, the graph is rising, so you would write that as the limit as x approaches pi over 2 from the left, tan x, that would equal infinity. And if you're approaching from the right, for tan x, got my x there, that's negative infinity. You can see that here. If you're on the right side of this asymptote, the graph is dropping downwards. Towards negative infinity, going downward. Okay, so that would be the second one. Okay, cosecant. Now cosecant by definition is 1 over sine. So we're doing the same argument as before, the vertical asymptotes will be wherever sine x is 0. Okay, so vertical asymptote wherever sine x is equal to 0. So this would basically state that the vertex, or the the vertical asymptotes are at x equals, and then we have 0 degrees, we have 180 degrees, we have 360, basically any multiple of 180. So negative 180, 0, 180, 360, dot 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 in both directions. So just basically 180n, where n is an integer. So I'm going to go ahead and write x equals pi n. These are the vertical asymptotes. Okay, what do the graphs look like? Well, these graphs also periodic. The first asymptote is here at 0 pi. The next one is at 1 pi. The one after that is at 2 pi, and so on. And actually, oops, I dropped my pencil. Exciting moment there in Mr. Shore's life. Okay. We have branches that look like this. One upward and one downward. So this is at pi, and this is at 2 pi. And this is sort of the footprint for the whole graph. Other pieces are equivalent to this one. So you would have another pair of these further over here between 2 pi and 3 pi. There'd be a branch like this, and between 3 pi and 4 pi, a branch like that. And this extends this way as well. And so on. But you can see that as you approach pi, let's say from the right, left side, it goes to infinity. If you approach pi from the right side, it drops to negative infinity. It's the same behavior we had with tan x. So we can write our conclusion. The limit as x approaches pi from the left is infinity, because it's going upward. And the limit as x approaches pi from the right, cosecant x is negative infinity. Okay, getting a little tight on space here. Let's go back to this one. Alright, for this one, the numerator and the denominator don't reduce, and the denominator is 0 when x is 0. Okay, so we simply have a vertical asymptote at x equals 0. It's similar to a up above. So if we do a limit as x approaches 0 from the left, plugging in 0 in a numerator gives us, well, you can't plug in 0, but if you plug in small values for cosine x, like cosine 0.000001, which is very close to cosine 0, comes out to about 1. And it doesn't matter if it's a slightly negative number that we're using for x or a slightly positive number that we're using for x. That doesn't matter. Cosine x, if you remember, is an even function. So basically cosine of 0.00000001 comes out to about 1. And same if you have cosine of negative 0.00000001, that comes out to about 1. But the denominator is going to behave the way that this one did. Large values on part A there. Okay, so this turns out actually to be infinity, and so does the limit from the right. Okay, so there it is. The top actually is insignificant. They're both 1. With small values, they're approximately 1. The denominators are what matter here. And so this problem basically behaves almost identically to the first one. Okay, let's look at this one. You always have to be careful with these because you never know when something might reduce. So let's go ahead and take a look at this one. Let's look at the bottom there and see if that thing factors. Okay, so let's break it into 2x and x. Alright, let's go with minus 3 here and a plus 1 there. Okay, so it factors. Alright, does it reduce? It does not reduce. Okay, so that means that both of these denominator factors represent vertical asymptotes. Okay, so domain restricts x equals, you said 2x plus 1 equal to 0, and x minus 3 equal to 0. We get two values, x equals negative 1/2, and x equals 3. These are both vertical asymptotes. Okay, let's check the behavior on these. Okay, let's do the limit as x approaches negative 1/2 from the left. And if you don't mind, I'll just write f of x here. I don't want to rewrite that horrible function. Okay, is it going to be infinity or negative infinity? Well, we know it's one of those two, right? And then we're also going to have to do this from the right. And then we're going to have to do the same thing for 3. Okay, so x equals 3. Let's write out our options here. X goes to 3 from the left and the right. Okay, so hopefully you see what we're doing. We're trying to check the limit on both sides of each asymptote. So we really have 4 problems to work on here. Alright, it might just be helpful to see the graph. It'd be nice to just have that graph handy so you can see the behavior. But one thing you can also do is just look at your values here. You do have an x-intercept, or excuse me, you do have an asymptote at negative 1/2, so even just a rough sketch would allow us to draw that, right? And then we have one at 3, so 1, 2, 3. We also know that the numerator here is 0 when x is 1, so that implies that there's an x-intercept there, and that is the only one. So that's helpful. So if we could just really plug in, let's say, negative 1, alright, and maybe, let's say, negative 0.9 even, we would know if this graph was going up or if it was going down. See? And then the same thing on this side. We could plug in like 2.9, we could plug in like 3.1, just to check that behavior on either side. Okay, so let's take a look here. Alright, well, it turns out that the graph goes like this here and upwards on this side. Alright. And then over here, the graph goes this way and this way. So my graph is not to any extent accurate. I mean, I'm not graphing detailed graph here, but the behavior of the graph is such as this. And you can look on your calculator screen to verify that. Alright, so basically if you're coming from the left on this function, it's approaching infinity. I'm sorry, for this asymptote. If you're coming from the right, it's negative infinity. And it's, for this one, it's the other way around. If you're coming from the left, it's infinity. If you're coming from the right, it's negative infinity. Okay, the last part of this lesson deals with seeing limits as x goes to positive or negative infinity. Okay, so this actually goes back to a should not really have had this on day 2. This really goes back to dealing with going all the way out to infinity on the right, or going all the way out to infinity on the left, and trying to understand that. So sometimes a function is complicated, and you'll have that limit as x goes to infinity down here, like that, or it's negative infinity or something. And it turns out that you can't determine that value, or you can't determine that behavior very, very well, let's say. This is not a vertical asymptote question, okay? So understand that we're revisiting extreme behaviors left and right, the way we did on the day 1 portion. Okay, so this is the example they gave us in the text. This is a very clever problem. The question is saying, what happens if I plug in infinity into here, or large numbers? And we know that this would be small, but we know that small values here for a sign generally means that sign is going to come out to about 0. We don't want to make an assumption that it does. Sign can be anything between -1 and 1, so it could just be obvious to you that this comes out to be 0 in the end, but the more convincing argument would be this. Let's change this into a limit where this is a finite number. Okay, so what we're going to do is we're going to take the reciprocal of a large number, which is approximately 0, and this is a large positive number, so we'll call it a 0 plus. And then we'll take the reciprocal of the inside here, which is just x, and we rewrite the problem entirely. The limit as x goes to 0 from the right of sine x. Okay, now if you can do a limit by simply plugging in the value down here, then do so. So you're not really allowed to plug in infinity. It doesn't really make sense to say that. Remember, infinity is not a real number. We opened the lesson with that. But by changing this to a finite problem, reciprocating a large number gives us 0, and it's a positive number, so it's 0 from the right. And reciprocating the argument here, 1 over x, to call it x, gives us a finite limit problem. And we are allowed to plug in 0 here to see what happens. So it turns out it's sine of 0, which is 0. If you're asked to do limit to negative infinity of, say, sine x, sine of 1 over x, again, you could change this to be, imagine, -1 trillion. Well, that would be sine of 1 over -1 trillion. So what's that? Well, it's very, 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 very small number. Slightly negative number, very slightly negative. Just to the left of 0 on the number line, -0.000000001, and you're doing sine of that. Okay, well, why don't we just reciprocate? Let's change this to mean 1 over a very, very small, very, very large negative number. So this basically is going to become 0, but slightly negative. That'll flip over and just be x. So we're going to evaluate this limit at infinity by changing this to be a slightly negative number and treating this as just x. And this is just sine 0 equals 0. Okay, so boy, that seemed like a little bit of hand waving, a little bit of hocus pocus there, illegitimate math, whatever you want to call it, but it isn't. Our rule for this is the following. We can evaluate a limit where this is a plus or a minus infinity by evaluating the limit approaches 0 of f of 1 over x. And if there is another, in this particular problem up above, we just had the 1x there in the problem, so we went ahead and reciprocated, making that a 1 over x. So it's 1 over 1 over x, which is x. But if there are other x's, you need to put in 1 over x's for each of those. Okay. So that's actually a technique that we can use. And you know, it could be 0 from the right or 0 from the left, respectively, depending on if it's plus or minus infinity. How often we use something like this? Well, depends, but hopefully you understand the logic behind it. And so we'll hang on to that. That'd be something good to put on our sheet here as we continue to make a list of things that we will memorize. And don't forget to write your sentences.